Welcome everybody to Tuesday night. You may think that it's a different day, but it is always Tuesday on this channel. I'm your host, MC Toon, and I've got a debate with Richard Wilde. Now commented on um, he had commented on Facebook who wants to debate about Earth's motion or movement or something. I don't remember the exact details, but
Yeah, something.
he's here. Welcome, Richard. He doesn't have his
Hello.
his video working, so I'll put up a thumbnail in the meantime while we talk.
Yeah,
But
unfortunately, this is my first time streaming, so I do apologize that I haven't got it or the technical difficulties ironed out. But I can share my screen, and that is the most important thing. So I guess we can proceed with that.
all right,
Um, yeah, so I'm looking forward to the a little discussion we've got going, and hopefully we can meet some consensus in the middle. I'm willing to have my opinion change, so
me too.
I'm looking forward to it.
All right, I how about you introduce yourself and I'll get a picture of you on the screen.
Okay, so yeah, not much to say really. So I work mainly in analytics, so well, Google Ads. So that's my profession. So a lot of looking at data, big data sets, kind of drawing a picture of where to put investments for companies and kind of pitch to them where they should invest their money to make more money. So that's kind of what I do on a day to day. And then I've just not long ago got into like the flat Earth debate, just kind of looking into bits and bobs that have been floating around the internet, some of which I found very interesting, and I thought, it's kind of grabbing onto me a little bit, and yeah, so I'm here now trying to have some questions answered. I tried having some questions answered in one of the chats that I was in on Facebook, and I got a lot of hate from that. um, so yeah, then I put the little bit of a topic out there that's let's have a bit of a debate on stuff that's a more reasonable discussion rather than just throwing insults out there. So that's kind of where I am and why we're here today, really. So,
Yeah.
and then you agreed to go on the debate, and I thought, yeah, why not? It'll be fun.
All right. Let me guess where you're from. I'm gonna play a little My
Go
Fair
on.
Lady here. Um, are you from Yorkshire?
Yes, but that's not a hard guess, seeing as Yorkshire makes up most of the UK, but well,
What?
England. But yes, I am from Yorkshire.
All right.
Technically, I am, but technically, I'm not because it's actually Derbyshire where I'm located, but I have a Yorkshire postcode, so my area code's Yorkshire. But
I'm
I
gonna
am
t-
actually classed as being a
I'm gonna
Derbyshire.
take it. I'm gonna take it.
I'll let you have that. Well done. Whereabouts are you from?
I'm in Minnesota,
Minnesota.
and some people call it a Canada Light, but they're wrong. Um,
Right. Okay. Why did they say that?
uh, well, because we border Canada to our north,
Right.
and Canada is America's hat, and
Yeah.
Canada. I mean, you guys get to tell Canada what to do. Still, we've had 250 some years of saying "nuh-uh" to you. So, I mean, Canada can't talk to us about
Well,
that.
we all get dictated by the Economic Forum, don't we? So whatever we tell Canada, it's coming down from somewhere else. So.
I don't know. I until recently the queen bossed you around is all I know.
Yeah.
All
Now
right.
we get
Oh,
bossed around by it. Go
Axis
on.
Axis and Penny are here. Penny is Axis's daughter. Hello, Penny. All right. Well, we have a little bit of a format. It's we each it's going to be 10 minutes, right, where we lay out our case. So you wanted to
Yeah.
go first. So you and then I'll lay out my case, and then we talk. Is
Yeah,
that
that
fun?
sounds cool.
All
I'll
right?
don't worry, I'll draw the short straw. Going first.
All right. And I'll set a timer, and you'll hear it. It's not really loud, but it's loud
Yeah,
enough
I'm
that
gonna
you'll
set
just
one
kind of
as well,
you'll hear it going.
just so I know where we are,
Yeah,
because I have a tendency to go over
yeah. And we're not
things
gonna
like
we're not
that.
gonna be super strict, but we don't want to go super.
Okay,
Just keep going and going. It gets to be too much. All right. Whenever you're ready, and you can present, and I'll put it up on my screen.
cool. Sorry, just bear with.
Bearing.
10 minutes in it.
Yeah. In it. 10 minutes
Isn't
in
it?
it.
Yeah, we don't speak proper English in Yorkshire.
I saw that TV show of the superheroes that talked like that in England.
Oh yeah, I know what you mean. That's a bit further south than where I am, but um, there's got an Irish guy in that though. He's a cool guy.
All right.
Yeah,
They
so
can see what you're presenting. So
cool. Yeah, we'll get started then. I think. So I'm already a minute in, but I'm going to reset my clock.
all right.
But cool. So yeah, is the Earth revolving around the sun the topic of the debate? So obviously, where to start other than the famous Michelson-Morley experiment, the greatest failed experiment? And I left a little quote here for you all to read. But so a renowned physicist basically saying that yes, a lot of research has been carried out concerning the influence of the Earth's movement. The results were always negative. So cool. I have got. I'm not. I believe that your audience is probably familiar with this experiment, so I did put a bit of a video in there, but I'm going to leave this for now and just continue. But I'm hoping the audience can just, if they don't know what this experiment is, go research it, go look at it. Basically, what they did, they shot two beams of light perpendicular to one another. One beam of light in the motion of the Earth, the other against the motion of the Earth. They did predict a 30 kilometer per second phase shift. That was not what came back from the experiment. What they actually found was a fringe shift, which they called a null result. So basically, what they thought at the time, with concluding the experiment, was that the Earth was stationary. So we can get into a bit more about that. So what happened next? They threw the ether out. However, even after throwing the ether out, because I know Michael will comment on this, so after throwing the ether out, they still had to explain why the light wasn't behind the other light. So I can't demonstrate this right now because I was planning to do this on my camera. But basically, if you've got point A, point B, if point A is moving as the light's traveling to point A to point B, back to point A, and if that position's moving towards point B, then the light will have to have traveled less distance than if the 2 points were stationary or not moving. So basically, the difference between the lights should have been different, right? But they were the same. So this was a big problem. So yeah, so then I just put another quote here. I know how much you love quotes, Mike, so I thought I will fluster you with a lot of these. So the problem now faced science was considerable, for there seemed to be only three alternatives. The first was the Earth was standing still, and we all know if the Earth's standing still, it has to be flat. So we'll proceed from there. So then basically what happened was they came up with a theory that the reason why that the two beams of light came back and there wasn't any shift and it was a no result is because in the direction of light or direction of motion, that the object actually contracted in the direction of motion, which was just the right amount so that then you wasn't able to detect the phase shift that was predicted. So then the Lorentz contraction was born as Lorentz, pun intended, as Lorentz was the one that kind of came out with that idea. So introducing Lorentz contraction into special relativity. So basically, this is page 63 of the general and special relativity paper, where they basically go against the empirical evidence. And I highlighted it right there, so you can read through this. I can share this presentation; it's fine, and there's a reference there as well to find this and read it in its full thing. But basically, a fact very perplexing to physicists. Lorentz and Fitzgerald rescued the theory. They rescued the theory, very important, because we're getting away from the actual empirical evidence now, and we're moving towards pseudoscience, theoretical physics. So they rescued the theory from this difficulty by assuming that the motion of the body relative to the ether produces a contraction of the body in the direction of motion. So basically, summarizing, contrary to the empirical evidence, they replaced it with calculative assumption. So and I think that's all I wanted to say on that. So basically, another quote there. The reason they didn't entertain this idea of a stationary Earth is because it goes against the Copernican principle, and obviously they didn't want to admit that for whatever reason they have built into their justification for that, probably because they're religious. I don't know. That's just what's floating around the internet right now. So then moving on. How reliable was the experiment? So someone that works with data a lot like it would be insane for me to bet against the data. So the experiment, it's been done a lot. They've done, and they get the same result every time. So for me, investing money into a company and I'm betting against that, then that would be pretty insane. And I just wanted to highlight a bit what Einstein, a quote Einstein said. So yes, they did do the experiment a lot. They got the same result. So I just wanted to quote Einstein here by saying insanity is doing the same thing over and over and expecting different results. But they didn't like the results. So they did things over and over again, tried to manipulate the variables, but still kept getting the same result with a slight change in fringe shift. But we can discuss about that. So the experiment was said to be 10 times more sensitive than required. The findings of their experiment was the building blocks of special relativity as the Lorentz contraction formula, the same mechanics used for the Michelson-Gale-Pearson, which discovered the sidereal rotation with a 98% accuracy. So basically, it should have predicted the Earth's motion around the sun, or at least if the Earth was moving, it should have predicted some form of motion if it was moving. And then there's another quote here by another renowned physicist. The experiment was 10 times more sensitive than it needed to be, blah, 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 blah. That the Earth is in orbit, motion around the sun. It didn't detect it. So yeah, again, you can go and find these people, read these quotes, and you can put your own thought process behind that. But that's where I am with this. So why was it accepted? So there's another paper here. Again, you can go look at this. And basically, the conclusion of this paper was it was expected because it was accepted, because it was the only experiment that could really, or the only phenomenon, should I say, that could really explain why the two beams of light came back with no fringe shift. So that's the only reason they accepted it. And again, it's nothing that we can prove. It's not testable. It's not repeatable. So it is philosophy. And then we just look at some quotes from Einstein. So I was familiar with the strange results of Michelson experiment while I was still a student pondering these problems, blah, 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 blah. We'll go on. This insight actually provided the first route that led me to now what we call the principle of special relativity. So that's a very important point, because the fact that these two beams of light came back at the same time, he's saying here that, he did consider this, and it was basically the foundation and the building blocks of his theory of gravity. So it's a very important experiment. I've since come to believe that although the Earth revolves around the sun, its motion cannot be ascertained through experiments using light. He goes on to say in other quotes, terrestrial experiments, all attempts of this nature led to a negative result. And then another quote, since then I've come to believe that the motion of the Earth cannot be detected by any optical experiment. So very interesting. Moving on. So again, what time are we on? I'll try and wrap it up pretty quick. So how physics moved away from science into philosophy. So yes, we're now in an era of theoretical physics, which is just ideas formulated to put mathematical calculations into placeholders, which will make what we see and observe true, projected onto a globe. So I think that it's not always, there's lots of interpretations and reifications going on with this. So it's not actually gives you a full story of what's actually happening, because obviously it doesn't reflect reality when you start talking about things like dark energy, dark matter. But then this is basically the guy saying, he's basically I can construct you a spherically symmetrical universe with the universe at its center, and you cannot disprove it based on observations. So you can only exclude it on philosophical grounds. So very interesting quote there. And then he admits here, we are using philosophical criteria in choosing our models. And a lot of cosmologists try to hide that, but he's not ashamed of that. So that's, it seems quite acceptable now. But obviously back then when he made this quote, people didn't really want to accept swapping out science for philosophy. So there was obviously a reason behind why he said that. And then going on to the Sagnac effect. So this is very interesting for just all intents and purposes, because my time's running out and I want to get to this point. Basically, we picked up sidereal rotation with 98% accuracy. According to relativity, we shouldn't have detected this because of the Michelson-Morley experiment. However, they did detect it. So then we came to another assumption that if the Earth was traveling in a linear path and the bending and warping was of space-time, kind of created the shortest path but it was actually traveling a linear path, so it went circular, even though that doesn't kind of make sense in itself. But they said it wouldn't be detected, which is why they explain why the Michelson-Morley experiment can be detected, but the Michelson no, sorry, the Michelson-Morley can't be detected, and the Michelson-Gale-Pearson could be. But then in a study in 2005, they actually found out linear motion can be detected, and I have the paper here as well, so we can have a look at that. And this is basically what it said. It is believed that the Sagnac effect exists only in a circular motion. However, we've discovered that any moving path contributes to the total phase difference. Yeah, and just another quick experiment, what they did, including Aries failure. So basically, the prediction wasn't what they wanted it to be. This is what they had to predict. So it was 30 arc seconds. But yeah, again, so another experiment that they assumed that the sky was moving and the Earth was stationary. And then, yeah, my time's run out, so I'll probably just wrap it up pretty quick. I wanted to go on to Miller and his stuff, but we can talk about that. And yeah, I think then, and I've just got a bit of a summary, but yeah, basically, yeah, I have my time's run out, so it's fine. I'll stop sharing there. But yeah, there's a bit more I wanted to get on, but yeah. Okay. Whose wits it? Did I? Perhaps that's just what the interpretation should have been. Cool.
My microphone was muted. They didn't hear me talking about you parroting Witsit. That's all right.
Oh, that's good.
It's beside the point.
Whoever Wits it is. I'm not sure. I've never heard of the guy.
All right. All right. Let me. I'll start my timer here. So here I have the book you were talking about. It's not a paper. Witsit made the same mistake that you did. He called this book a paper. It's not a paper. It's a book. Right here.
Paper.
Right here. Yeah, it's printed on paper, but it's not a paper. He didn't submit it to a journal. Right here. Chapter 16. We refer to the yearly movement of the apparent position of the fixed stars resulting from the motion of the Earth round the stars, aberration, and to the influence of the radial components of the relative motions of the fixed stars with respect to the Earth on the color of the light reaching us from them. That is Einstein's references to how we know that the Earth is orbiting the sun. And then the part that one of the parts you picked is a little bit later there in the same book here. Now, what are those two things? I'll cover those two things here. I have them on screen. Aberration right here. He's speaking specifically about what James Bradley discovered in 1725 to 1727, published published in 1727. It came out. He measured a shift in the apparent position of the stars based on what time of year it is and what position in the celestial sphere they are. And the stars that were at the top of the celestial sphere, specifically Eltanin, he started by measuring, and that's 75 degrees in the ecliptic plane. And since 90 is the dead center at the top of the ecliptic plane, it has a very nearly circular path. And then as stars are closer to the ecliptic equator, they have a more and more elliptical path, and it gets more and more flattened. And I can show you an example here. There's these circles here on the right side there. And so that bottom one, that's just a line. So things that are on the ecliptic, equator of the celestial sphere have a line, and at the top there we have a circle that would be at the 90 degrees in the sphere. So those are due to parallax, or sorry, not parallax. Definitely not parallax. Definitely aberration. So here's a little zoom in on it. This is interesting. If you look, here's the position of the Earth around the sun. We have A on the left and B on the bottom, and the sun is in the middle. This line up here is this not to scale drawing of this to the star, but that's the apparent position, and it's hard to read. But A is at the bottom, not at the left side. B is at the right, not at the bottom. It's 90 degrees out of phase with the position of the sun, or the position of the Earth around the sun. Very interesting part to that. Now, I've covered this before, but the aberration is kind of described like this: when you're standing in rain with an umbrella over you, not moving, everything comes down. But as soon as you start moving, your feet will get wet unless you tip the umbrella forward. And so when you're doing that from somebody outside the reference point of the person with the umbrella, that's what the middle picture is there. You see the rain coming straight down and the person being kept dry. And then on the right side there, if you're moving with the umbrella person, it appears to you that the rain is moving and that the person is stationary. So that's what we're seeing with the light coming to us from the stars because of our motion relative. So there's a little diagram, shows the direction of Earth's motion. It looks like the star is in front of the motion there. And then this is the another picture of the Earth around the sun there with pointing. These are pointing straight up into the ecliptic. So there's one. The second that he was talking about was the annual Doppler shift. The annual Doppler shift was published by Vogel and Schneier in 1887. So around when Einstein was born, certainly Einstein had plenty of time to read through this. Their publication is on my website here. It's a 350-page book written in German. I won't read it. It would be like Vogon poetry to me. But anyway, here's a short summary in English from History of Astronomy by A. Panikek. Huygens was the first to determine, according to Doppler's principle, the radial velocity of a star through the displacement of its spectral lines. And then I'll jump down to, here we go, in 1887, Vogel and Schneier at the Potsdam Observatory constructed a spectrograph with proper provisions against the flexure and change of temperature. Now the results had such greater clarity that the orbital velocity of the Earth was clearly shown by a periodic change in the measured radial velocity of the stars. So there's the second thing Einstein was talking about. I'll add into it a third one, that stellar parallax has been measured. 1839, Friedrich Bessel did that. He wrote, this paper is in German, but he measured the parallax of 61 Cygni to 0.314 arc seconds. Now, in 1727, James Bradley measured to a 1/10 of a degree accuracy aberration. So this is more than 100 years later, and Bessel measured to up to 1/1000th of an arc second in precision there. So pretty good 100 years of technology improvements. Since then, we've had quite a few more. This final, let's see which one here in 18, there it is. Parallaxes of this from Professor Henderson. So he was in South Africa. Here's his paper. He listed he listed 20 stars that he had identified and measured the parallax for. Here's the table of them right there. An average, there's a bunch, just since there's 20 of them, there's an average of 0.39 arc seconds per. They range from 0.01 arc seconds to much higher, like this Alpha Phoenicius was 0.9. But it wasn't, he noted the ones that were high, he didn't have a strong weight. He didn't like those. He preferred to look at the ones that he had a stronger weight for, a better measurement. So there are the three ways that prior to Michelson-Morley or Einstein, people were certain about the movement of the Earth around the sun. People, if they want, they can have a look at this. Somebody said Vogon poetry. Who doesn't like Vogon poetry? Anyway, there's three different ways that we know the motion of the Earth around the sun. So I'll leave it at that because I directly addressed the motion, and I won't go into things like, newer ways, because they mostly involve putting things on top of rockets and putting them in orbit and outside the Earth's orbit. So there you go. I have about 2 minutes to spare.
So is this your rebuttal?
No, that was my
That,
presentation.
that was your presentation. Okay.
Yeah.
Right. And now you're going ahead with your rebuttal to my presentation.
Yes. Okay. So, your presentation was about. I'm rather familiar with it because I'm familiar with Witsit, who you seem to not know.
I don't
know
seem
how
to know who this guy is.
I don't know how you could not know him, because your presentation was almost word for word his presentation. No kidding.
Yeah, I don't know about that, but yeah.
All right. You said Michelson Morley concluded that the Earth was stationary. So I have right up on the screen right now, I have the Michelson Morley paper. Do you know what page they concluded the Earth was stationary on in this paper?
So the fringe shift that wasn't detected was a good piece of evidence to indicate that the Earth was actually not in movement.
Yeah, but you said specifically when you in your presentation, you specifically said that they concluded that the Earth was stationary in their paper.
I never said that they concluded it was stationary. What I was getting at is the experiment. What you can get from that experiment, that we didn't observe a moving body, and then the rest of the presentations go on about, even though actually my presentation was more to do with actually showing that the belief that they put on top of that with the Lorentz contraction, even though if you took, if you take this type of experiment that was very accurate predicting sidereal rotation, but then didn't predict the movement, but then you could quite easily look through the quotes and then
let me get back to my rebuttal then, and we in our open discussion we can do this. So yeah, we can do this. I get that I've read this paper. Nowhere in there does it conclude that the Earth is stationary. You mentioned Einstein in his book. He said rescued the theory, that Lorentz rescued the theory, but you missed the context, and Witsit missed the context too. The theory that was rescued was the aether theory, or the ether theory, and Lorentz's attempt to rescue it was Lorentz contraction, that he was claiming that things actually physically, really, in our reality, contracted, and that was how he attempted to rescue the ether theory in light of Michelson Morley's no fringe shift that they measured. So it wasn't trying to rescue anything else. They were trying to keep intact the theory of the luminiferous ether, or sometimes it's in Airy's Failures paper. It's called the undulating theory of light. So that's a very important distinction that if you're not reading all of it in context, you tend to miss. Now, you mentioned pseudoscience. Pseudoscience is not thinking about things and having a hypothesis. Pseudoscience is things that are not testable. Chapter 3 and 4 in Popper's book, The Logic of Scientific Discovery, talks about that. It's not the only absolute way to measure things, but that's kind of a general guideline. If it's not testable, then it very well could be pseudoscience, or not falsifiable. But if you have a hypothesis and it's testable, then it's testable, so it qualifies as a potentially scientific. You said that Michelson-Gale should have no predicted motion. Something about that it shouldn't. Now Michelson-Gale was measuring the effect on light of Earth's daily rotation, and so I don't know why anything would have predicted no motion. In fact, relativity, the special theory of relativity specifically, predicts a Michelson-Gale, and it's a Sagnac type observation or measurement that there should be a fringe shift because the speed of light is the same in all reference frames. So when you move, it's a rectangle. So Michelson Gale had a rectangle of multiple kilometers in length, and the whole thing with the Earth moved while the light was going around the loop there in both directions. So one had a longer path from when it left until when it got to the end, and one had a shorter path from when it left until it got to the end, because while the light was in transit, the entire apparatus rotated. So special relativity specifically predicts that will happen. So it's completely in line with special relativity. And then I'll ask you, and when we get to our discussion, we can talk about it. I'll just ask for you to tell us what is meant when Einstein talks about the word terrestrial experiments. So that's my rebuttal, and I didn't do a timer, and I think we were going to do 5 minutes, but
Yeah, you went over, but I'll let you off.
all right. Well, anyway, I guess
I'm nice like that, you see.
Your turn for a rebuttal.
Cool. Yeah, let me just reset my timer. Cool. Yeah. So my rebuttal. Right. So so the model used to make these observations, I've already shown the foundations of which are based on assumptions. Not only that, the models are built, they're basically reverse engineering the sky and then kind of projected that onto a globe. In addition, Einstein, Wolfgang Pauli, Stephen Hawking, they all admit you can't prove the Earth is orbiting from the Earth, as you would get the same effects. So yeah, and including stellar aberration. So these observations aren't exclusive to the globe. So, for example, parallax. So, if you I know you like frisbee. So, imagine you got a frisbee in your hand. You put it above your head, and you can mark out point A, B, and C in like a triangle formation. As you spin that frisbee around, you could see that point A would match up to point B and point C, depending of where you've actually positioned the frisbee. So, even if the shell above the Earth, as Einstein calls it, then you could actually still get parallax. So I don't think that's a rebuttal in itself, because that observation is still actually apparent on a flat Earth with the rotating shell above. And then you spoke about stellar aberration as well. So again, it's like, I think it comes down to like reference frames. So when we're looking at these starts, like how do we determine which is moving? Is it us moving, or is it the object in the sky that's moving? How do we come to that determination? So that's my answer to that. And then I think also talking about like epicycles, and I know that speaking to a physicist on this actually, and I know that they don't like the idea of epicycles because they think it's a bit clunky. But actually, if you the epicycles is actually a direct reflect. It's a reflect holographic projection on a magnet, like what you would see. And I know the flat Earth kind of idea is, there's a torus field, and it's like there's kind of like a magnetic declination that kind of that rolls around. And actually, the idea of epicycles and like kind of looking at the idea of Mars on that, it does actually work on a flat Earth, and the idea of like it's magnetism, and we've got the center North Pole. So yeah, how much time? So I'm halfway through. So yeah, looking at the sky, actually, if we actually dive like into the whole sky and the redshifts and looking at the universe, actually debunks the globe, in my opinion. Like everything points to the Earth at being at the center. You can only map out 4% of the universe because the model is so wrong. We have to invoke dark energy and dark matter and all these fictitious forces which have never been proven to this day. So coming back to where you said it can be testable and repeatable, then and it can be observed. Well, dark energy, dark matter, and all that stuff can't. So yeah, that's by your own definition, that is actually pseudoscience, and they only do that for the maths to work out. So also when there's other areas of so basically the expansion rate. So they had to invoke younger dark energy as well, because again, even after invoking all these other assumptions, younger dark energy was another thing that they had to invoke, because when they actually went further back, they could see even there was it didn't match out. So basically, yeah, they had to invoke that. We can discuss more about that. But even with that idea, actually violates the conservation of energy principle as well. So they went as far as to name, yeah. So they also went as far as to naming the cosmic microwave background anomalies, the axis of evil, which also shown the Earth at the center. And then there's the flatness problem. So actually looking at the skies, I know there's the argument that you presented, it actually debunks, oh, there's a lot of evidence, we have to evoke a lot of pseudoscience. If you don't like that word, we can talk about it. We can say we unlock to evoke a theoretical physics for the maths to work out, which it still doesn't kind of work out. So yeah, overall, if the sky's moving in the Earth stationary, you get all the same effects. The globe answers all the pseudoscience antithetical to the empirical evidence and works fine on the flat Earth because you don't have the dark energy problem. And if you want me to prove it, I will. Just give me £80 million as NASA's budget, and I'll be happy to. And that's me done.
All right. Well, I can tell you for certain that James Bradley did not have that kind of budget. Neither did Bessel.
I never said they did.
All of it, but yeah. So you don't need NASA's budget to do it. They didn't have NASA's budget to do it. So you said that you can get the same effects for flat Earth. I've heard the claim that you can get the same effects for flat Earth, but I've never seen the presentation of how the same effects happen for flat Earth. How does that happen?
Well, you could get parallax on. So you discussed parallax. So I was just reiterating the point that actually you would get parallax if the shell of the Earth was rotating above you. So
the shell of the Earth?
The shell over the Earth.
Okay.
Sorry.
But now so parallax, yeah, but parallax is an apparent motion of some stars in relation to other stars.
Yeah.
So why are some stars moving and others not?
I can't answer that question, and I think it's a good, valid question.
But hold on, you said you can explain it using the flat Earth model. Now you can't. It's fine that you can't, but you can't claim that you can explain it and then say you can't.
What I said was that there was actually what I said was these observations that you see in the sky. What they've shown is that they basically took those observations and then kind of reversed engineered it to how it would work on a globe. And then I mentioned parallax. So that was kind of a secondary point. It wasn't actually built into the same point. But then I mentioned parallax, and I said that actually parallax would occur if the shell of the Earth was rotating above you, because if you marked out point A, B, and C and you move the shell, you would actually see that they would align up. And again, it's still quite hard to distinct parallax in a globe model, because you've still got the problem of knowing what is moving. Is it you that's moving, or is it the sky that's moving? So there's still a relationship there that it's not exclusive to the globe. So that was kind of the point I was making.
All right, but you didn't explain. I just want to make it clear, you did not explain how some stars move and some don't for parallax.
I'll need to think about that, and I'll come back to you on that one.
All right,
it's not something...
because that's one of the three things that I mentioned, right? You have parallax, you have aberration, and parallax is select stars moving with a varying amount, and it doesn't relate to where they are. It apparently relates to how far away they are from the Earth. Aberration is due to their position in the ecliptic sphere. So if they're at the poles of the ecliptic sphere, right, 90 degrees declination north or south, then they are a circle. And if they're on the equator of the ecliptic sphere, they have just a line, and everywhere in between is a varying ellipse of different foci. So that's a second motion that has to be accounted for. There's others, but those two are the ones that I referenced. And then the third is the annual shift in the Doppler, depending on, and different stars have it based on where they are, again, in the ecliptic. As we're moving, one direction while we're moving towards some stars and away from other stars, some have a shift one way, some have a shift the other way. 6 months later, which stars are shifted is reversed, and in between it had a sine wave relationship of how much it shifted. So all of those, there's an explanation for for the globe and the Earth orbiting the sun. There isn't one that you've presented, and you're like, well, they just reverse engineered it. Well, yeah, that's what science is. You see something, you're like, oh, I wonder how that works. Let me put together a hypothesis. Okay, there's our hypothesis. Let's go test it. Okay, that didn't work. Well, let's try a different hypothesis. Okay, that didn't work either. Let's try another one. Oh, that one did work. Okay, so we have some progress here. We think that we have a little better understanding. So then you go and explore the fringes and the the different variations of that particular hypothesis. That's what you explained as, I don't know what exact words you use. Maybe sometimes they use reverse engineer. But yeah, that's what you do. You see something, you have a hypothesis for what's causing it or why or how it's happening, and then you explore it. That's just science.
Yeah, I get it. So the exact reason why these stars move, I can't give an answer on that because obviously I don't know actually what's causing that, but I think it's probably something to do with, well, I actually can't say. I have my opinions on that, but it's not embedded in science. So I'm going to leave that for now and I'll research more on that. But basically the point that I want to get to is, yes, I do agree with what you're saying. The stars do move in a particular way, but if you're using that, you're saying that because some of these stars are moving this certain way and it reflects your model, but you've got 95% of the universe that doesn't work. So you may have a little bit of the universe that works, but the rest of it doesn't. But and again,
like
if you want to,
you don't have an explanation for that either. So you have an explanation for less than we do. So it's not really helping your case.
No, but like I say, like we discussed whether the Earth is going around the sun, right? So, and you're saying that because you get a parallax effect, and I get the point, right? So I get it. Like you one time of the year the Earth is on the opposite side of the sun, so then when you're looking at a star, it appears parallax. So yeah, I get what you're saying, but you could still get that same effect if, like as I said before, if the disk above you if the stars above you was rotating, point A can actually match up to point B and can actually match up to point C, depending on how fast it's rotating. Well, not how fast, but where it is in the rotation. So, and just to go to your other point as well. So, yes, I agree. I think Mars is a very good example as well with what I know, because I was talking to my friend about this and he was talking about Mars, but epicycles is something that does actually work, and it is a good, like I said, it reflects a holographic projection of a magnet. So how the stars move is a bit of a mystery to me, but I think as I start looking into it and I start correlating that with how like the projections of what we see and like what I said with the holographic projections of a magnet, there seems to be some correlation there. So that's quite interesting, Richard, to me.
Tell everybody, tell the audience, who have you heard these things from? 500 people listening right now. Who is it that you have picked these things up from?
Yeah, I've picked stuff up. I don't need to say where I've picked it up from. It's all right.
I mean, you've already denied that it was the one that I know that you got it from. But put a name to who it is that you got these from.
It's all right. I don't need you to go out and chase after these people that I speak to.
I've already spoken to them several times.
Okay. No, it's fine. It's fine. We're just discussing the theory,
dude, just
right?
Pretending you don't know who Wissett is funny. I get it. But you're totally.
No, I admit, I've heard of him. I've watched some of his videos, but I've not.
Dude, you are 100% copying everything he said. The toroidal field.
No,
yep.
It's quite a big thing out there now. So everyone's talking about that at the moment.
But, I mean, seriously, anyway, it's his script. It's his. You just listed his script. Yes, it's the best.
So I've got a question for you now. I've got a question for you now.
I have to say, I have to give you props. It is the best parroting of his script I've seen. Right, a lot of the other like Dearth completely screws it up. He can't even copy Witsett at all. And you nailed it.
Who's Dave? Who's Dave?
Oh my gosh,
is that Dave?
Flat Earth Dave. Yes,
Dave. Flat Earth Dave. Right. All right. Yeah, like I say, I've not been into this, so I've only really just discovered this, so I found this quite interesting. So, I'm sorry that I don't know all the players yet, but by name. But yeah, I do. I can know him. But
all right,
But yeah, I've got a question for you now then, because
Okay.
I've let you
All right.
you answered the first question. So my question to you is: do you think the Earth is moving in a circular motion or a linear path?
It's going in an orbit around the sun. Yeah, that's an
Yeah. So do you
elliptical.
think that's a
It,
circular path or a
it
linear path?
it's elliptical, but it's nearly circular. How about that?
So you're saying it's a circular path?
No, I'm saying it's elliptical.
Okay, so it has to be a circular path or a linear path.
No, it's an elliptical path.
Right. So you've made up your own idea of it then. So
No,
you said that about me, and now you've just made up your own.
no. Why do you think it has to be linear or circular?
Because when they discovered the Sagnac effect, and they found out that actually we should have detected what was happening in the Michelson-Morley, the 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 reason they used it, they didn't detect it because what they said was that the Earth was moving around the sun in a linear path.
In Michelson Gale, you think that they said that?
That was kind of
I mean,
something that.
you're looking right now at Michelson Morley. Do you think that I can't just pull up Michelson Gale? Hold on.
Yeah.
Hold on.
So they.
So here we go. Here we go.
Okay.
What page? What page has it? There it is. What page
So
has what you're saying?
I've got a reference here for you that says it. So we can go to this. How do I drop you this link?
No. You said in Michelson Gale. This is it. We're looking at Michelson Gale right now. So where in Michelson Gale did they say something about Earth's orbit around the sun?
So I've got the generalized Sagnac effect. This is by I can't pronounce his name. So excuse me, but his name's Ruong Wang, 2004. And what they said were,
All right, you
it
can
is
send
believed
it.
the Sagnac effect exists only in a circular motion.
Send it. I'll bring it up on screen.
Okay.
You can send it on Messenger.
Bear with me a sec.
And you said his name is Ruhif? That's a good name. That's a good name. Fairy Muff wonders if you keep the ravens at the Leeds Armory. I don't know what that means. I don't know what the Leeds Armory is. I suppose would be an armory in Leeds. But I don't know what the ravens are.
Yeah, Leeds is just so I'm just trying to find this point. I'm
Okay,
I'm just reading through the paper now.
I know. I'm well, no, send it. I'll get it up while you're reading it.
It's believed.
It'll take me a minute to pull it up. Let's see. All right, I'm gonna look up the Leeds Armory.
Yeah. How can I send this to you?
On Facebook Messenger.
Send it on Facebook. All right.
Just pop it in there, and I'll oh, there it is. All right. All right, we'll see if the first law is confirmed here, huh? All right, generalized Sagnac effect by Ruyang Wang and some other people in St. Cloud, Minnesota. Look at that. Not far from in 2004. They may not be there anymore. I could drive up there and say hi to them. Experiments were conducted to study light propagation in a light waveguide loop consisting of linearly and circularly moving segments. We found that any segment of the loop contributes to the total phase difference between two propagating light beams in the loop. The contribution is proportional to the product of the moving velocity. Okay, so this is there it is. Yep. There is the.
So if you scroll up.
Scroll up, okay.
Yeah, I'm just trying to find it again. Scroll down. Wait, scroll up a bit. Sorry,
Wait.
Yeah, there it is. Just go to there. It is believed.
It is believed that the Sagnac effect exists only in circular motion. However, we've discovered that any moving path contributes to the total phase difference between two counterpropagating light beams in the loop. In a previous experiment using a fiber optic conveyor, FOC, we showed our preliminary results that a segment of linearly moving glass fiber contributes delta theta equals here, this equation here, right? 4 pi VL over C lambda to the phase difference. And there's the reference 6. Here we generalize our finding of the Sagnac effect with a more complete and study, find a series of new experiments. Right?
Yeah, so they said that they could actually detect it in both a circular motion and a
in a linear motion.
Linear.
Okay, so here's the diagram here is an interesting one. So here they have this the optical fiber there around two wheels, right? And they're actually moving the wheels, so the whole fiber is moving along with it, and then the actual fiber optic gyroscope there on the bottom is sliding along the conveyor, because when you're rotating the wheel, the two wheels, the length, you can't just have the gyroscope be same position, because the fibers then you'd have to have slop on either side, and that might affect it. So that's what they did there. But what they, and so the problem is here is this is something moving, right? And
Yeah.
they measured movement in something moving.
Yeah.
And their point of this, the main point of this, I've read this paper. The main point of this was that they're talking about, rather than the Michelson-Morley and the existing Sagnac effect, was talking about the enclosed area inside the loop. And they're proposing a different mechanism, which is based on the length of the actual linear length rather than the enclosed area. But it doesn't change anything that they're still measuring this motion, right?
Yeah, I'm not. I think, yeah, I believe they are measuring the motion. Yeah.
Yeah. So the Sagnac effect measures motion, and when there's no motion, they don't measure motion. That there's no fringe shift. So I don't quite know what you're trying to get at, because this doesn't quite support your claim, because Michelson-Gale measured motion, even though it was sitting on the surface of the Earth, not moving on a wheel or anything like this. It was just sitting there. They had bolted it down. It's sitting on concrete platforms near Chicago.
Yep. So then the question is, so why didn't the Michelson-Morley?
Because Michelson-Morley wasn't a rectangle. It was essentially two straight lines in an L shape. It wasn't exactly that. They bounced it back and forth and stuff.
So you didn't think that it should have...
Michelson-Morley did not enclose any space. Michelson-Gale did enclose space, because it was a different geometry of the experiment.
Right. So why wasn't... So they did actually say, obviously they did go and invent the Lorentz contraction to explain for that reason. So it was they did actually was meant to be there.
For Michelson-Morley?
Yeah, the Michelson-Morley experiment. So it was actually meant to be there. It's just that they didn't detect it.
Yeah, with the presumption of the luminiferous ether. So that's one of the assumptions going in, and so of course Michelson-Morley, here's the thing. It's the name of it. Well, right in the title, it says on the relative motion of the Earth and the luminiferous ether. So they're measuring the effect of the motion of the Earth in the luminiferous ether, and they were presuming that the ether existed.
But even with or without the ether, you still had to explain for why the two light beams arrived at the same time.
You do, and special relativity explains why it didn't.
Yeah, with the Lorentz contraction, which is my point, that it's the Lorentz contraction is nothing that's actually been tested or proven. It's because obviously they say that the measuring device contracts as you try to measure it, so you can't actually detect it.
No. That is again, that goes back to
I've got a video here where he explains it, so he might be wrong in the video, and that's where I got my information from on this. So
yeah, and I think I know that guy rejects relativity too, but But yeah, you can
Well,
play
I
it
can
in a
play the
second. But
video,
yeah, hold on a second.
but
Let me say my
I
point.
still think you have to explain why the light beams arrived and there was no result. I think you still have to explain that.
Yeah,
And I
and
think that
yeah, and
they
so
explained it,
let me.
even with or without the ether. I still think you have to explain that.
All right. Well, let me explain this then. You said, yeah, rescued the theory. That was the one. It's in this book. Rescued the theory.
Yeah.
The theory that Lorentz was rescuing. Lorentz and Fizel
Fitzgerald.
or Maxwell, was it? Anyway, it was primarily
No,
Lorentz.
it
He
was
gets great.
Lorenz and Fitzgerald. Yeah.
Fitzgerald. Okay.
Yeah.
Was the ether the actual the ether theory, and he proposed that the ether caused the objects moving through the ether to physically contract. And Einstein in the book goes and says, well, but there's no reason for that to happen. It doesn't make any sense in an electromagnetic sense that actual physical objects would compress, and all things would compress equally, right? And so steel would compress the same amount as a fluffy pillow. That
Yeah.
doesn't make sense. So, all right, you have you want to send me the link, or do you want to share it?
Oh,
Share
what do
your
you mean the
screen.
video?
Yeah, the video.
Yeah, I could play. I could play it, but
Okay.
I just want to reiterate the point that even with the ether or without the ether, they still had to explain why the lights didn't. Sorry, they did return at the same time. They still had to explain that with or
Yes.
without the ether.
Yes.
So you're not giving me an explanation for that. You're just saying that they
Oh,
threw the ether out, but
yeah.
it's still not explaining why they still had to explain for the light not being
Sure.
the
Okay.
result.
Yeah, and I can explain that is that
Okay.
light travels at the same rate in all reference frames. So in our reference frame, light is moving at one velocity. And so it doesn't matter where it is in relation to the sun. Within our reference frame, it moves that same. So you have that the L shape, right? It goes this direction, the same
Sorry,
velocity as this direction. Now, relativity says that for an observer at the sun, right, who's relatively stationary in relation to the sun, the Earth appears to that person, not actually is, but appears to that person to be compressed in that direction. But also at the same time, an observer in our reference frame doesn't have that experience, but instead to us, the person that's stationary relative to the sun, they appear to be compressed.
So how did they prove that?
And a third observer who is at a completely different velocity, is compressed in a yet a different quantity. And then these are all, Lorentz got the numbers right, but he was applying it to the wrong thing. And so relativity, special relativity, and then general relativity later,
Yeah, I think
brought those together. So how did they go through that? Great question. And so
Yes.
I have on my website, mc2net/relativity, some of the key experiments that confirmed these different aspects of relativity, because
Okay, I'll be interested to hear about those.
yeah, there's lots of, I'll send you the links so that you can look at. I mean, not right now. It's
Can you explain just
so yeah.
sake.
So here is, so Eddington 1919 isn't to this point, because you're talking about special relativity. This is more about general relativity. Kennedy Thorndike gets a bit into the relativity of time, which again isn't quite special relativity. I mean, they all kind of go together. What is more specific? Yeah, Ives Stilwell, I think, is and Pound Rebka.
So what did they do?
No, sorry,
how did that
Keating.
explain the
So all right,
the null result?
well, I explained the no result already. It was, it's that the speed of light is the same in all reference frames.
Yeah, but again, you still had to explain that why the light wasn't behind the other light. So then I thought you was going to show me an experiment of how the Lorentz contraction formula is justified.
Yeah. So I gave you the explanation. You're just asking for the empirical validation.
Yeah, I want
Okay.
the experiment that they did to prove that.
So all right, let's look at Haefel-Keating here. So Haefel-Keating, it's not exactly it. It's this is more about time dilation, which is to general relativity, right? So this is a broader test than the specific special relativity. But so that the Haefel-Keating, they had four very accurate clocks. Two of them they left on the at the lab, and two of them they put in an airplane. They flew around the world one direction, and then they flew around the world in the opposite direction.
Oh, so you talked about time dilation.
Yeah, yep, time dilation. So the clocks are accurate to this amount. I put lots of zeros in there, 10 to the negative 14. And then they had a specific prediction based on relativity that the clocks going one direction would be 40 nanoseconds.
So are these the quantum clocks in this experiment?
These are their cesium clocks, so they're measuring the fluctuations in a cesium atom. Yeah. So 40 nanoseconds going eastward, and 275 gained 275 nanoseconds going westward. That's the prediction. And then the observation was that it lost 59 plus or minus 10. So the margin of errors are important here. Lost 59 plus or minus 10, and it gained 273 plus or minus 7. And you'll find that the margins overlap on the predictions and the observations in both instances.
So what are you saying here is you say that time slowed down? Actual time.
Yeah, time slowed down for the clocks that were going one direction, and the stationary clocks, or the clocks sit in the lab, slowed down when the
so this is actual evidence that you're presenting, where you're saying that they actually showed how time, us being on Earth, flying from where they're flying from. Sorry.
They were in a lab in the United States. I can pull up the paper here where they cover where it was.
The atomic clocks. Yeah, I've actually seen this before, and I know that part of the clocks there was something in this paper where it said the clocks actually weren't even accurate, or there was something wrong with the clocks.
What page was it on?
I can't remember now, but I have had a look at this, and there was something there. Someone was showing it me, and they were saying that there was something wrong with the clocks, that they weren't actually accurate.
All right. Well, I'd have to see where that was from.
I'll have to dig that up, because I can't remember at the top of my head, but I know that there was actually an explanation for why the clocks did act the way they did.
Yeah.
All right. Well, it wasn't actually consistent either when this experiment was done again.
All right. Well, there are some other experiments afterwards, so that did the same test. So testable, repeatable. It was repeatable.
So your claim is basically that time slowed down is why those two light beams came together at the same time, because it slowed down.
It's part of the broader general relativity theory that it was a confirmation of that.
That's fair.
So,
I don't buy it, but I respect that you've done. Obviously, you know more than about that on me on them clocks. I can't really say. I know that I do think they did that experiment a few times, and it wasn't a consistent result. So I do think it says somewhere in one of the papers that the clocks weren't actually accurate, and there was not fault, but it wasn't as it should have been as they took it. But I'll let you have that one. Even though I still don't think that explains why a beam of lights returned at the same time. But
well, I mean, I explained it, and I don't know why that would be an improper explanation. You may say you reject the empirical.
So it was because what I explained with the Sagnac effect. So they did actually when you shooting something in a linear path, they can actually measure the fringe, shall we say?
They can actually measure the fringe, or they cannot?
They can.
Cannot. All right.
In the
That
Sagnac
I
effect,
mean that's what.
not the
Oh,
Michelson.
in the Sagnac. I mean,
Yeah, sorry if I weren't clear on that.
to be clear, relativity predicts that a rotating thing like the Sagnac experiment, Michelson Gale, will measure a fringe shift.
I
And
know they've got mathematical placeholders to explain that experiment, but that's not the same as saying it will predict it,
yeah,
because
it predicts it. It totally
it
predicts.
predicts it based on the mathematical placeholders that are put in.
That's what prediction means. That,
But
that's how you do a
the
prediction.
prediction has got to be an experiment, and then you do the experiment, and you can test the independent variable and change that and manipulate that, and then you get the prediction. Obviously, the prediction that they made was that um, the light beam should have returned at the rate that it didn't return at. So
Why
you're
would you say that
using,
the prediction is different? That wasn't.
because for example, the Michelson-Morley prediction was that the light beam, well, they should have detected the Earth moving around the sun at a certain rate, which it was 30 kilometers per second,
With
which
and it has a
detect.
presumption.
So
Remember, there's a.
then they put these placeholders in place. Placeholders in place. They put the placeholders to kind of reverse engineer that to kind of make it make sense. And that's how I understand it.
All right. Well, I would say maybe your understanding of it is maybe.
Yeah. Perhaps I'll research more about that, and we can
use an
discuss
update.
this. But yeah, you like, by all means, send me papers and highlight the bits. It'll be useful because yeah.
Well, I mean, I
I'll
sent
point
you
you
the
to where
link.
to
I sent you the link
yeah.
to Relativity that has a list of the key experiments, like typically the first experiment that confirmed a an aspect of relativity, and then I mean you can find your own repetitions of these experiments, and except for
Yeah.
Gravity Probe B, I think um, that that one is just. I don't know if I don't think I listed it. Yeah, I didn't list it yet. But Gravity Probe B is one that just is finishing up now, and it's the first test of a particular thing. So,
Cool.
All right.
Um, on your intro, I was listed, and I did have questions I wanted to ask you, but I didn't write them down. I only started writing them down towards the end because I started getting a lot of questions. So
Okay.
I forgot the whole presentation now. But yeah, that's interesting. How long is it? What time's it been? Oh bloody hell! It's been an hour.
It's been an hour. Now I have a hard stop in 90 minutes.
Right. Okay. I could just shotgun you some stuff, and you can give me some answers. We don't need to debate about it, and I'm interested to hear the rebuttals that you have.
Sure.
Cool. I've got, so the Aries failure is an interesting one. So they said that they should have measured up to, I forgot that top of my head. I've got a slide here. Is it 38 seconds of arc? But they measured 0.8. So the conclusion, because obviously they filled the telescope up with water, and then they could see that the light didn't enter the center of the telescope. So the conclusion was that actually the sky was moving and the Earth was stationary. That was kind of the conclusion. So what's your explanation for that?
Well, that wasn't their conclusion. All right, so here it is. The name of the experiment is not Aries failure. Airy did not name that. Aries failure.
Well, that's just the kind of.
I know it's gotten that name. The name is on the supposed alteration of the amount of astronomical aberration of light produced by the passage of the light through a considerable thickness of refracting medium.
I could have just said that, I could have said that, but it's a bit of a mouthful.
It's so catchy. Is it my favorite part though? Is the name of the person from the continent that they are testing his hypothesis from? Remember his name?
No.
Klinkerfuse.
Oh yeah, Klinkerfuse spelled.
There it is.
Klinke. Yeah, fuse. Yeah.
I love that name. Professor Klinkerfuse maintained that as a necessary result of the undulating theory. So this undulating theory, that is the theory of ether. When they say that, that's what this is. Luminiferous ether is undulating theory. The amount of aberration would be increased. So he's saying with the test of undulating theory, that's what they're testing here. They're testing ether. that the amount of aberration would be increased in accordance with the formula which he'd given. And so we tested it with the following experiment, or he supported it by the following experiment. And then Klinkerfues described it, and then this is what Aries did. So Klinkerfues had computed the effect of the 8-inch column of water. Observation appeared to show the aberration was really increased by 7.1 arc seconds. Right? They put that 7 quote, double quote there, .1. They swap the angle of that. I think that's funny. Anyway, and so they're testing here this Gamma Draconis, which is the same one that James Bradley tested in 1725 to 1727. Same star. And they choose that star because it's always visible from England. Yeah, the same star by which the existence of the laws of aberration were first established. The position of the star is at present somewhat more favorable than it was in the time of Bradley. That's because, you know why? Why is it in a more favorable position? Do you know why?
No, I'll let you tell me.
Well, it says it right here. Because it's moving. It's moving. The star's position is moving in the sky. That's why. I don't know if there are many flat earthers that claim that stars don't move, but I mean, right here it says it. It's in a better spot 100 some years later. It's 1871, so it's like 150 years later.
Well,
Anyway,
we can see the stars move. Like, I think that's an observation that we can. Well, not moving like how the planets move, but like we could see them at least rotate around Polaris, so to speak.
yeah, but this is talking about the proper motion. That the location of a Gamma Draconis in the sky in relation to other stars. So they often talk about background stars. So there's some stars that don't move. That's because they're really far away. They're so far away that their position doesn't appear to move over time. It's so slight that we can't measure its movement. But there are closer ones like Gamma Draconis, whose position does move because of its relationship between us, the star, and the background stars. The classic example is Bernard's star has the highest proper motion, but Gamma Draconis has a decent amount. Anyway, the point was that they can see it better because its position is a little more convenient for their observatory in England. All right.
Okay,
anyway,
so how does that prove that it's the Earth that's moving and not the sky? Because you just said they prove the stars are moving. So that's kind of the point.
Yeah, what this does is this falsifies the theory of the falsifies the undulating theory, right?
Which is the ether theory.
Which is the luminiferous ether. So that's why they call it a failure, because he was hoping to confirm it, because that was the popular common position, was that there was this ether. So
don't you find it funny though that every experiment that doesn't go the way they want it to, they say it's that the greatest failed experiment? Or don't you find that quite funny? I do.
I don't know.
I mean, so for example, so the Michelson-Morley experiment. That's because I wanted to talk a bit about the ether now, because you mentioned the ether.
Okay, let me. I found the final part here.
Yeah.
Let me just read it. I think myself justifying in concluding that the hypothesis of Professor Klinkerfues is untenable. So there it is. He's saying it doesn't match observation. So all right.
So how do you find Dayton Miller? Is that his name? Dayton Miller's. I'd say his experiments, but he didn't really. He just kept repeating the same experiment. So how do you find, do you find that interesting, or do you know what I mean? I might explain. Dayton Miller basically.
How about you explain for the audience, because I know what you're talking
Dayton
about,
Miller,
but they don't.
Yeah, it did. It basically repeated the Michelson-Morley experiment over and over again, in different conditions, and kept getting the same results. So it was, and basically they was talking about the ether, weren't they? And they was trying to kind of falsify the ether. So people were saying that he wasn't controlling the temperature, and other various things. So then, for example, he went to a higher altitude. He controlled the temperature variable and then kept getting all the same results. And he found correlations with altitude, the time of the year, and direction. Those were like three things that he found correlations with. So his understanding, and which I think is, it's obviously we can never be 100% certain with our understandings, but his understanding, it makes sense to me. They I've got a quote here actually somewhere. So the effect of the ether drift have persisted throughout. After considering all the possible sources of error, they've always remained a positive effect. So
do you have?
kind of
I want to pull up the Dayton Miller write up. Let's see. I think I have.
Based on how many times I can't remember how many times he did the experiment. He did it a lot, but he kept detecting the fringe shift. So it's obviously for the globe to be true, we can't detect anything. So he could never get it to zero. He was always detecting some sort of phase or fringe, however you want to describe it. He was always detecting something. So yeah, what would you think's going on there?
All right. Well, let's pull it up first, right? Because we want people to be able to see what it is you're talking about. All right, I'm getting it. I'm getting Dayton Miller's paper. I think it was 1934. The ether drift experiment and the determination of the absolute motion of the Earth. Right? Is that the one you're talking about? He published more than one, but this was in published in Nature. So
let me have a look. One sec.
New sheep unit. A commander shepherd looks after 10 flocks of sheep. I'd like a pan-galactic gargle blaster if we're having Vogue on poetry. 1934.
No, it's not the same one. 1928 with the one.
1928. Well, hold on a second here.
There's that. I'm trying to find. There's so much flat earth stuff on my computer preparing for this debate.
So, and he just So Dayton Miller 19. So the problem is there's no title. That one he didn't give a good title for it. So hold on. Go to Google Scholar.
Anyway, that was what he thought based on that. But I'm just wanting to hear, like, we don't have to go through the paper. Yeah, I just want to know what your thoughts are, or like what other evidences that you think that prove him wrong on being able to find correlations between altitude, year, and direction.
Well, like I said, I just want to pull it up. Give me a second.
Okay.
I mean, you don't have it ready. That's fine, but I need to. I want to pull it up so that we can have a look at it. Citation, related papers. I mean, you don't have the DOI link. The problem is, so I'm my one reference here is, it says Dayton Miller, 1928, Astrophysics Journal. Number 5 for the year. So 1933. See, all right. Well, let's. Do you have the specific one you're thinking of? I don't want to spend half an hour hunting down a specific.
I don't know, somewhere. I've got a load of crap here. I was lucky to find that other one. To be fair, it was just there, it jumped straight out of me.
All right. Well, I'll do one more check here.
So sorry, what are you looking for in that paper?
I'm looking for the paper that you're talking about by Dayton Miller.
Where he says he found like correlations with how high they went.
I mean, I just want to pull it up on screen,
right,
so we can look at it. All right, conference on the Michelson-Morley experiment held at the Mount Wilson Observatory, Pasadena, California. This might be it here.
You can send me the paper if you want. When you find it later on, and you can just give me what you think.
All obviously, right. Is this it here? 1928. The presence of Michelson and
I have seen this
Lorenz
one. I was trying to think if it was this one.
In the early months of 1927, offered an exceptional opportunity for a conference on the theoretical practical aspects of the Michelson-Morley experiment. That seem
I
right?
think so. I think so.
Um,
1 sec.
so all right. So what he did for people at home, he did do multiple iterations of the Michelson-Morley experiment, basically, and he used some of the same apparatus even. He did it at the Mount Wilson Observatory in Pasadena, California. And so what he concluded from this was that he thinks that the Earth is moving through the ether, and that he thinks that he measured the movement of the Earth through the ether. Now, I don't know why you want to reference this, because his conclusion is Earth is moving, ether exists. That's his conclusion. He did not. If you're accepting his position, you are not agreeing that the Earth
I think
is
just
stationary.
for all
You are.
intents and purposes. Sorry, can I just explain? Like,
Oh, sure.
just for all intents and purposes, like you don't have to agree with someone's conclusion to take their experiment. And this is like the same, but obviously across all regions. Like I'm quite aware how like academia works. I have actually got a master's degree, so I know that you don't have to agree with someone's opinion to take part of their work to use that to back up an alternative opinion. Because generally the experiments that they do are very good. They were very well conducted, and obviously everyone can conclude different things from that. So I don't want to just be like, just because you don't agree with his opinion, you've got to rule out everything else that is done. I don't agree with that whatsoever, and you will lose me at that point. Sorry.
All
So
right.
I
So
don't
all
want to
right.
go down that route.
So then you do agree. Then I mean, well, what part do you agree with? That he did measure
But
a fringe shift?
yeah, I find it interesting that the for the globe, what the globe lot were saying, or I've been in that group now. Everyone's been like globers, flat earthers. It's like whatever. So whatever, like so. There's a portion of people what they were saying where they obviously that with fully behind the Einstein's theory and whatnot. They were they were saying that they shouldn't have picked up, or there shouldn't be a fringe shift. It should be null, and kind of why that's why the idea of it being a null result. So I find it interesting how this data Miller went out and kept repeating the experiment, but never got an actual true no result, and was still detecting this fringe shift. So I find that interesting, and I know that for the kind of
Okay.
people kind of say that that is the ether that they're picking up in those experiments, so it can never be null because there's an ether background.
Okay. But
Yeah.
so my question then again is, you agree in the part of, because it sounds like you're just basically cherry picking, then you're selecting what parts you want to agree with. Are you agreeing with the part where he measured that there was a fringe shift?
Well, what the measuring apparatus detected, yeah, there was something there that detected something. Some people want to argue that it didn't detect it. It was just like instrument error or bending warp from space time or whatever they say. Some people want to argue that. Whereas my point of view and my perspective is that I think these devices were very accurate. I think that if there was something there, then it would pick it up. If there wasn't, it wouldn't pick it up.
Yeah,
That's how
but
I
I'm
see
still
things.
I'm still trying to get to this. So if you're
So
agreeing,
what is it that it picked up? Interesting. I don't know.
yes, what is he
Ether,
picking up?
an ether is an explanation. Oh yeah, electromagnetic radiated background radiation, or some electromagnetic medium or whatever it is surrounding.
So you don't. I mean, it sounds like you don't know what he's picking up, but just that you want
But there is. I
to
don't.
conclude
I
that the
can't say
ether
that I do know
exists.
what I picked. But people say that an ether is an explanation for that, which I think if there is an explanation there, so I will go with that explanation for now.
Yeah,
There may be
but I mean,
other.
right here we're looking at. I mean, it's the Earth's movement around the sun is what he claims that he was measuring. That's what he claimed, and these fringe shifts are claiming that. But the problem is though that he didn't.
But
He's not the last one to do this experiment, right?
sorry, so are you talking about when they were trying to excuse me, when they were trying to measure the motion around the sun, the fringe shift was different, so they should have picked up a 30 kilometer per second fringe shift, but what they actually picked up was somewhere between 0 and 10 kilometers. So what I'm speaking about is that zero between the 0 and 10. So it's not It's not the motion of it's not the Earth orbiting the sun, because obviously that wasn't what was predicted, but they did pick up something. So what is that? Because obviously that's not the motion around the sun, because they came back and everyone admitted that it wasn't it, because it was a null result, and then Lorentz contraction, blah, blah, blah. So what is it then? So there's something there, and it's not as predicted, but there is something there. And I think the people in your paradigm, what they say is that, I think later on they said it was bending and warping of space-time or something like that. But I think the initial conclusion was that it was just the instrumental error, and it wasn't actually picking up anything. It was just because the instruments weren't calibrated correctly.
All right. Well, here's and I'll send this to you. Here's a reanalysis of Dayton's work. So, I mean, you kind of blundered into. I mean, his claim is from his conclusion is that he was measuring the motion of the Earth through the ether, and you're saying no. You're claiming he was not measuring the motion of the Earth through the ether. He's measuring something else that's nebulous and you can't identify. No, but you're definitely certain that the ether exists. But anyway, here is. No, I'm not going to go into it. Here's an analysis.
I can explain that again, because that's not what I said at all.
They went into a deep analysis of the actual data. He did store a lot of data points, and it made it really nice for these people to be able to analyze it. I'm not going to go into it right now, but I put the link in the live chat, and I sent you the link. So again, let me number just one, number two. Hold on. I got it. You got a lot of time. I need it.
Because you misrepresented what I said, and now you're making an argument behind.
Well, let me
something that I didn't say.
Finish
and
this.
You've done that a couple of times this debate, and I've been patient now. It's annoying.
All right. Let me. So that was 1920 something and 1930 something, right? So that wasn't the only time that it was done. So here's a more recent one that was done in 2007, another 2008. 2009, all of them much more precise than
all picked up fringe shifts
than Gale, much more precise than Gale could do, and the fringe shifts that they identified were within the margin of error of the instruments. So 10 to their margin of error down in this last one here is 10 to the negative 17 level. So super precise. So their measurements are significantly under the error bars of anything that Dayton was measuring. But anyway, what's your position then on what Dayton Miller was actually measuring?
So my position was, it's not what Dayton Miller concluded. He ran the experiments, and my position is that it was interesting that wherever or however he ran the experiments, he always detected this fringe shift, not the fringe shift that I mentioned, that the Earth going around the sun, not that fringe shift. He measured a much smaller fringe shift, which obviously they said should have been instrumental error. So, but whatever they did, they couldn't, they couldn't remove the fringe shift. So there was always something. It was always picking something up. And so my point is, it's interesting why these super high tech, this high tech equipment, super precise, and I worked a lot with micrometers, and so I understand how precise these things are. And to me, it's just an easy cop out to say, oh, it's instrumental error or it's bending and warping of space time. It did pick something up, because I can tell you from experience of using micrometers and stuff, if there's nothing there, you don't pick it up. There's got to be something there for it to pick
this
it up.
Isn't a micrometer though. It's not that simple.
I know it's not a micrometer, and I'm not saying it is a micrometer. So please, I'm just using an analogy to kind of say,
now,
look,
if your micrometer had 20 more decimal points on the measurement,
these things are way more precise than micrometers. They are way more precise, and micrometers are very precise, and you can get a very good measurement out of them to then, obviously build stuff. But so basically these gyroscopes are what they was using. It's kind of a gyroscope. It was picking something up.
No, the Michelson-Morley style experiment is not a gyroscope. It's an L shape, so it can't measure rotation.
Well, it was using light, so you get what I mean anyway. But the point is that it's picking something up. I find that very interesting. There is something there. There's something in the background. Yeah, interferometer. Yeah,
the word you're looking for. So
yeah.
All right. Anyway, so the analysis of it here. 23-page paper here, It's not just hand waving it away. They actually analyzed the data. They did a lot of work. This is a pretty serious paper here. Talking about the 1933 paper. This is right here. Oh, I closed it. Crud.
So just out of interest, why have they said that they're so you said that the what's it called? The apparatus had a margin of error. So basically a threshold of which it fell into, then they throw the data out basically.
No,
So
no,
how
no.
would they
They don't throw the data out. They just say, the noise, the fluctuations that are within that margin of error are insignificant.
So how did they come up with that margin of error?
That you have to analyze the stuff that you're working with, the apparatus that you're working with. So, there it is. Okay. Just a second. Because I closed the thing on accident. That was
That's all right.
There it is. All right. This is the 1933 or 1934 paper that this paper is analyzing, right? How do they do that? Well, for example, on a tape measure, right? A simpler case than even a micrometer. The thickness.
Yeah, so
of
they
the
need
line.
a reference point.
Yeah, the thickness of the line on the tape measure. You can't accurately expect to measure better than the thickness of that line. Right. So, and typically, it's not even that good, right? Because when
can you elaborate on that? What you're saying? They can't. Yeah, sorry, I'll let you go.
I would have been farther along. So let's say you have a tape measure and the line is I'm just 1/10 of a millimeter thick. You can't measure with that tape measure to 1/100th of a millimeter. That's one of the ways that you deal with your margin of error. But typically in a device, if they have gradations at a certain level, then 1/2 of that gradation is your minimum margin of error. So if you have lines every 1 millimeter, then your device is only accurate to 1/2 of a millimeter at best. Right.
Yeah.
And
then
I
get that plus or minus.
Yeah. So then when you do other things, you do things like some statistical analysis, you do least squares, you do you do a large number of other things in the process, and it's a lot of statistics that you do to determine your margin of error, and you find, well, how close were my measurements? If the measurements were all grouped within a very tight range, then you have a very nice looking standard deviation. And if they're scattered around, then you don't have as good of a standard deviation. So then when you report that, you say, well, that is plus or minus something based on the analysis that we did. And Dayton Miller had a large amount of measurements. Awesome. And when this paper went and analyzed them, it found that the things that he was doing in there was just noise. It wasn't that he found anything that was right.
But the apparatus was 10 times more sensitive to. So when you're talking about the plus or minus and the lines in between, like for example, the millimeters in between a centimeter, it was actually 10 times more sensitive. So actually, it was sensitive to actually pick up the accurate result.
Well, I mean, if you're going to just go for that, then
that's what it says. That's what they've said. They've said it was.
Then I'll just say, I mean, we've got one that's significantly more precise than that, 10 to the negative 17 level here. So this particular one is way.
You need to understand that when you're doing this precision measuring, then obviously that's better because you get a more granular result within the amount, but you'd still measure up to that point quite accurate within the fringe shift. What was it? It was somewhere between 0 and 10 kilometers per second or whatever it was. I can't remember now. My brain's a bit flustered because there's a lot of information, but basically because it was sensitive enough to pick it up without any margin of error.
But well, no, there's
10
always
times.
you can't say there's without a margin of error. As soon as you say without a margin of error, then it
Well,
shows that you
so
don't have
the margin
a
of error,
grasp on
sorry, the
metrology
margin
here.
of error that would come into this would be more of a human error rather than it is something wrong. If it's been calibrated correctly, if the measuring equipment's been calibrated correctly, then it's more of a human error that's coming in, taken into play rather than it is an actual apparatus
Well,
error.
let me encourage you
So if
to
you're
read
so yeah, I
to
get it.
read this
You
one.
can do the
Right.
you can work that out by repeating the experiment over and over again, and then you can actually
Which
work
was
out
done
what the
right here. Yeah.
the human error was.
Yep. And
Yeah, I get that,
that's
but
what
this
this
is a
did.
this is
That's what this did.
but you said it did it with the apparatus. It didn't do it with the human.
I encourage you to read this paper. I sent it to you. How about that?
Right.
What's your master's degree in?
It's business MBA,
Okay.
but you still have to analyze documents and present a case to get awarded. So yeah, I am well indoctrinated into the system. I just like to question things and be open minded. So that's why I'm here. I've also got a bachelor's degree in computer science as well. I think you have a similar background. You know?
I studied electrical engineering and computer science.
Did you?
I've written software. I've not
Right.
done electrical engineering for my career. So
My dad was an electrical engineer and a physics teacher, believe it or not.
is he still kicking?
Yeah, he's still about. He's retired now, though. He still does the odd thing here and there, but
You've
yeah.
not told him about this, have you? Because don't
Well, I've spoke to
don't.
my dad about bits, and he doesn't believe in the moon landing. He thinks that's not true. So I guess that's where my skepticism starts because he's like, oh, it's impossible. The technology they needed to get to the moon, you know, there's more in a mobile phone. I know people sometimes use that as a for it, and
That's a red herring.
but yeah, I get that, but he doesn't buy it, and I don't buy it because it's quite obviously fake, in my opinion, because you can just see like some of the footage. It's just terrible. But that's another discussion.
All right. Do you know what
People are invisible.
do you know what it would mean if somebody's asking if you keep the ravens at Leeds Armory?
You keep the ravens at Leeds Armory. Okay, so Leeds has an armory in the centre of Leeds. I've actually been, I visited it just recently with my wife, actually. The ravens, let me think. The ravens. It might be a type of like army or something. The ravens.
I think he's asking if you know any poets that might
Is this
have
the
written
same guy?
that might have written poems about ravens. Do you know of any,
I know any
poets that have written poems about ravens?
I don't know, man.
Maybe this raven said nevermore.
I don't know. You're gonna have to tell me.
All
I'm not
right.
sure what you're on about, to be honest.
All right, I'm just guessing here. See, all right, the Sun Express is it's like that's a quote mine that you were quote mining.
Go on, say it again. I didn't catch that.
The Sun Express thinks that you were quote mining.
The Sun Express.
The Sun Express is a commenter in the live chat here.
Okay.
Yeah.
Oh, so we're going on to comments now.
Well, all right. I have 20 minutes to a hard stop. So
yeah, go on then. We can go into comments. Right. Yeah, it's been an interesting chat. I appreciate your time anyway. So
all right,
we can go into comments, and my wife is probably wondering where I am now. So.
Yeah. Why are you talking to some wannabe Canadian at 20 to midnight here? I don't want to be a Canadian, people. I cannot say sorry enough.
What's wrong with Canadians?
What's that?
What's wrong with the Canadians?
Oh, nothing. They just I can't play hockey. I can't ice skate, so I probably would get rejected at the border if I tried to cross the border.
Right. So it's not a racist thing then.
No, Canadians are just as pasty sour cream white as me.
Yeah, true.
Have you never seen Canadians?
Well, yeah, kind of. Well, I've never been to Canada, but I kind of see them on the TV. But in Drake Canadian or something, Justin Bieber, they're Canadian, aren't they?
Beaver? I don't know.
You know, maybe. I think Drake is, but I don't really follow that scene. But
who's Drake?
the singer, rapper slash pop man.
Oh, I'm not much for rap.
Yeah, see,
All
but he's
right.
kind of everywhere, so you can't avoid him.
MB says
Where
how
have you
much.
been if you don't know who Drake is? Come on, Michael. We can do better than that.
I mean, the name rings a bell.
He
When you
went out
said
with
rapper,
Rihanna. You know who Rihanna is?
somebody that hangs out with Drake.
Yeah, just like a pop singer. You know who? Come on, you've got to know these people. Anyway, yeah.
I
Sorry,
know
I
who
digress.
Dave Mustaine is.
Dave Mustaine. Oh, Dave
Yeah,
Mustaine. Oh, great guitarist.
yeah.
Great. I loved it. I love Megadeth.
There you
Absolute
go.
classic
All
band.
right. Well, there we go. We're on some good footing now.
I've actually seen Dave Mustaine in real life. I got his autograph.
Oh, I've seen Megadeth a few times, but I didn't get his autograph.
I've never seen Megadeth. I only seen him because he went to a guitar conference. Because obviously you've seen from my profile picture, I play guitar.
Yeah.
So yeah, I went to visit him at a conference, and I got to shake his hand, and yeah, he signed my book somewhere, wherever it's knocking around somewhere. But
What
yeah,
what book was it?
it was just
Was it a book of poems
bit.
about ravens?
Ravens. Yeah, it was a Raven book. Got Dave Mustaine. Is this why that guy wants to know if I know
I
poems about ravens? Because he knows that I've got Dave Mustaine's autograph in my book.
all right. All right. MB says how much evidence of flat will be presented? None. Well, this wasn't about flat though, was it?
It was, to be fair, there is some good evidence out there. Whether or not you want to reject that, it's obviously up to you. But I've got one right here actually. But if you want to have a look
Nah,
at it, you
we'll
can.
have to schedule another one. How about that?
Yeah, but
All
we'll
right.
schedule that one. I'll need to learn what's going off in these papers that you've sent me, and then any more questions, we can have a quick one on that.
All right.
But
Tim
yeah,
Lynch says
questions.
insanity is doing the same thing over and over again, expecting different results. Something
Yeah,
Einstein never has been documented saying ever.
is it not? Is that not true? Because
I
everyone
think,
seems to quote that with Einstein saying that he said that.
yeah, but I do think that it seems to be a misquote.
Is it?
Yeah, it's probably
Interesting.
something that Abraham Lincoln said instead. Yeah, he said it. He said it on a Reddit thread the other day. Jiffwald gifted a membership. Paul Camish says, question for Richard. I'm currently waiting for the ISS to pass over the UK to speak through the ISS repeater on ham radio. Can you explain how do I do this?
I'm not sure.
But if he's
You tell
talking to
me.
people, on the ISS, how's that happen?
Oh, he's talking to people. Yeah, you can talk to people through mobile phones. It don't mean that they're on the ISS.
But he's not on a mobile phone. He's pointing his ham radio at a particular spot in the sky.
Mm. Yeah, I'm not sure. I'm not denying it could be something up. There's obviously something up there. It could be picking something up and transmitting. So if you point at the ISS, it's transmitting a signal somewhere else. That's quite a common thing that satellites do, or weather balloons or whatever you want to call them. But yeah, I don't think
Somewhere
that's
else.
evidence. It's interesting that I agree that that's interesting. It's certainly something to look into, but I don't think that's direct evidence to prove anything. But
I mean,
next question.
wow. All right. Timo Lynch says flat Earth has nothing to fear but sphere itself.
The sphere itself, I've heard that before. Funny.
Pat
Get
in the
new
chat.
jokes.
Pat in the chat. This is a good one. Pat in the chat says, I don't know why, but I find it hilarious that someone who has a similar accent to Brian Cox so confidently gets this material wrong.
First of all, I don't like Brian Cox.
Of course you
arrogant.
don't. Of course you don't.
And it's not the fact that we've got different opinions, because I really get along with people different and all kinds of opinions. That doesn't matter to me. He's just very arrogant, and yeah, it's just kind of like, ugh, throw up. Like we have different opinions, Michael, but I think we'll get along quite well. So we don't have to have the same opinions.
But what about having the accusation of having a similar accent?
He doesn't have a similar accent. It's completely different to my accent. Perhaps you think it's similar because you're not used to the British accent. I'm
It
not British. I'm a commoner. But yeah,
wait, hold on a
it's
second.
not the
What's the
same.
difference? You're a commoner,
Accents
you're
all
not
around
British.
England. Well, British is very like well, what I kind of refer it to being like I'm English like the Queen, the Queen's English, the British English, we've got the posh. Oh, I'll go and have a bath tonight, that kind of stuff. We don't talk like that.
Okay. Americans can't really tell, but we don't know.
Yeah, I
right?
think people just think we've got the same accent, but obviously when you're in the country,
I mean,
everyone's got
I
different
totally
accents.
nailed that you're from Yorkshire.
Yeah, I'll
And,
give you that one.
and I can and do you like Yorkshire pudding?
You know what? I was never a fan of Yorkshire pudding up till about a year ago, where I've started to like it now. So,
But now, am
have
I
you tried it
put?
before?
I believe that Yorkshire pudding is not actually a dessert item.
No, it's something that you have with. Do you know what a carvery is? I'm not sure what you call it in America, but yeah, like you've got your Thanksgiving dinner, haven't you? You'd have a Yorkshire pudding
Okay.
with like all your turkey,
You got to say
your
in it.
peas, your carrots, and
Gotta
it's
say
kind of
in it.
just like this piece of bread that's kind of I don't know how to explain
Okay.
it. It's like
All
flour.
right.
Usually,
All right. Icy Spin says, "Why does the sun rise over here and set over there?"
as a mental azimuth, as a mental grid of vision. There's your answer.
Oh my gosh, that is straight out of Witsit. That is 100% him. His nonsense. That
You seem
doesn't
to like Witsit, don't you? What? I've got
No,
a question for you,
no,
Michael. What do you think of Witsit?
Oh, he's funny. But I mean, it's just that you've completely said everything that he says. You've almost said almost nothing from other people.
Well, I have looked into what's his face? Nathan Oakley, but I really don't like that guy. So there's only so much of him you can watch. So
Yeah, I mean, you did one time say independent variable, and so that's little Oakley there. But I mean, one of the things that we do here is we try to figure out who the Papa Flurf is, and so we know that Witsit is your Papa Flurf. So
nah.
All right, so Ted Iacocca says he should stick to playing guitar and looking hip.
Looking hip. I'll take that as a compliment.
There you go.
Yeah, I'm not claiming to know everything about the world. I just find it interesting conversation. And yeah, that's why if I wanted to stay ignorant inside my own little shell, I would stay ignorant in my own little shell. And I think talking to other people's opinions is important. So, and I'm interested in the topic. Like my dad's a physics teacher. I've been brought up learning about this stuff. So it's always good to discuss things that you're interested in. But yeah, if you think I'm, what did he say? I can't remember what he said now.
Witsit
yeah,
is
go
your
check
Papa.
out my music.
Witsit
no,
is,
not that.
Oh,
about
hip.
me being a jive or something.
Hip.
Hip. I'm not a hipster, but yeah, I play a lot of guitar.
All right. The grumpy old mechanic says, "Don't forget the Compton generator." Of course, the Compton generator is one of the multiple ways to measure the rotation, the daily rotation of the Earth, which is different than the annual orbit of the Earth around the Sun. But
I'm writing that down. I'll look into that.
Yes.
Compton generator.
Yeah. Dave
Cool.
Kircher.
Thanks for that. Who was that?
That was the grumpy old mechanic.
Grumpy old mechanic. Laying it down. Cheers, dude. I'll look into that.
All right. I may have a link to that on my website on mc2.net/spin. Dave Kircher says, redacted, Whittycaca, it's Wounds Day.
Okay.
So the funniest lake in the world is Lake Titicaca.
Okay. I've never heard of that lake.
Yep.
Where is it?
It's in South America.
I bet it's a very popular lake.
Well, it's a funny name, lake. And
I bet people get there and they're very disappointed.
Yeah. I mean, they'd be sad that the first part is not there and happy that the second part is not there. But there is a frog native to only Lake Titicaca that's named the scrotum frog. No kidding.
Right. Okay. That would have been better if you didn't tell me that last bit. But
yep. Alyssum says, thanks, Bob. Earth rotates. End of argument. Uh, Brianna Johnson says new
Well, can I
sheep unit.
comment on that?
Oh,
Can I
sure,
comment
sure.
on
Go
that?
ahead.
So is this? I've been looking into this, and so is this? Did people say thanks, Bob, because of the gyroscope?
Yeah, because Bob
And
Nodell headed up the research that he was trying to do, and he was trying to prove, in his words, that the Earth was stationary. But his experiment that he was certain was going to totally vindicate him went the opposite of the direction he was requiring it to go.
so is that? Can you tell me a bit more about that? I'm actually generally interested, and I can't
So
really find much
so
information on that.
he somebody in the community spent $20,000 to purchase a fiber optic gyroscope, similar technology to the Saniac experiment there, from
Yeah.
Michelson Gale, but with three orthogonal loops in there, so it's measuring in three axes, and these are from an airplane, and he is a single engine certified pilot whose certification expired in the 70s, but he has a little bit of a background in aeronautics, and so he says, his words, they're very precise, they're very good at measuring rotation, and so they got one, and he put it on his desk and he plugged it in, and it measured rotation, 15 degrees per hour drift,
Right.
while it was just sitting at his desk. This very precise instrument that he said was very precise
Yeah.
measured a drift. So anyway, I don't generally pick on him anymore because he died. So
what does? Yeah, I heard about that. I'm sorry. Yeah, sorry to hear about that. R.I.P. Bob. But out of respect, even though I don't know anything about it. But so what? So he picked up. What did he pick up? You're saying he picked up Earth rotation.
It's a device that's specifically designed to measure rotation, and it measured rotation.
So what happens when you took it to a higher altitude? Because is this where they're saying that they're picking up the centrifugal or Coriolis forces coming down?
Right. He said a lot of words. He never did publish any details of what he did or how he did it or the methodology of it. He just said he brought it to a higher elevation and got a different magnitude of rotation, which doesn't support stationary Earth, right? It shows that there was some sort of an unexpected result, and so the people that do the bet, because he didn't publish anything, people say, well, they think that he changed the pressure faster than it was supposed to, or something like that.
But
Don't know. He never published anything.
Yeah, I understand, but the experiment itself is quite interesting because he took it to higher elevation, and the reading did it not get greater as he took it to higher elevation?
I don't know. He never published anything.
Yeah, I think that's what I've heard that
Yeah.
he did take, which is quite interesting if that is the case.
Well,
So
if that was the case, then they would be absolute garbage in airplanes, because airplanes go to higher elevation. Yet somehow they're still used in airplanes, and they're rather expensive. If they didn't work, you'd just not buy them. Right.
Well, I don't fully know what actually happened there, so I can't really comment on that.
And he never published anything.
I want to know what happened.
So, but now there's much better measurements of rotation on my website at mctuna.net/spin. Significantly more precise than his. Anyway,
sorry, what are those? What are those?
Different measurements of the rotation of the Earth.
Yeah, what? So, give me one.
Some of them are optical, using the Saniac effect. Another one, they use.
So that's the same as what's already been
similar to his, yeah. And so then another one is the Compton generator. One that I like is that they used a plastic sphere, a plastic ball. They used 15 Tesla magnetic field to levitate it. They got it spinning, and then they measured the variation in its rotation. I think they used a laser, and they got 15 degrees per hour change in rotation. So,
okay, what was that last one called?
That is, I'll pull it up here. People can see it. So mc2.net/spin. It's down here. It's called Detection of Earth's Rotation with a Diamagnetically Levitating Gyroscope. So I'll send you.
So
Send you
what's the difference between that and a normal gyroscope? You say this is the one that's specifically made for planes.
This no, this is a different. You asked me for some example of this of what I have on
Yeah,
this page. So this
yeah.
is that one that has a 15 Tesla magnetic field, and they got a 2 centimeter diameter plastic ball suspended in that field, and then they measured its variation of its rotation. There you go.
Okay. I'll if you want to send me
Yeah.
that, I'll have a look into that. That'll be good.
Yeah.
Because I still I don't I'm writing notes here, but I don't know what I'm writing on this one.
Yeah. All
I
right.
don't
So
know.
yeah, so I'll send you the whole thing here. The Rumpus says, to clarify on Bob Nodell, he says the fiber optic gyroscope is temperature sensitive, which of course it is, because it makes things expand and contract. And Bob took the device to different altitude, which had different temperatures, so he got confusing results. Yeah, so you need to control for confounding variables, and he did not. So
Right. Like I say, I can't speak on behalf of that because I don't know what happened there. So
yeah. All right, so let's see. Icy Spin says, what evidence would you need to change your mind?
well, like I say, I am leaning flat Earth, but there's nothing that can. I don't know what to say. Like it's hard to know for sure what's the truth in this because it's very like this is an interesting question actually because just initiating flat Earth to someone, then you get up a lot of hostility. So that in itself, I think, needs to just stop because
Hold on,
I think there's like
don't get away from the question.
Yeah, so that actually pushed me over to the other side because that says to me, if someone's so certain in their ideas, then why the hostility? For example,
go to Nathan Oakley's channel and ask that question.
Yeah, I don't
that
like
doesn't
that guy.
you don't get far with that line of reasoning.
No, but
right?
it's very much one leaning. Like Nathan Oakley is an exception. Everyone else is
no,
like
he's
really
not.
nice one.
No, there's a ton. Pig Slapper Oink.
I don't know who that is. So
SSUM on Twitter.
Anyway, I think
there's plenty of examples of people that are
there's a lot of
rude. So
I think there's a lot of censorship on that side, and I think that if it was an even table, for example, it was an even. Sorry, I've got a dry mouth. My water's run out. If it was an even battlefield, let's say, so to speak, then I'll probably be more inclined. Or I don't know. I don't know what I would think, but it does. There's an emotional side to me that says that they're trying to censor.
Let's go back to the question.
They call it science. They call it science. They're trying to censor it. So censorship and all this stuff that's going off, it does kind of push me in the other direction.
I got a time frame here. I'll tell you this. Sorry. I have a list of things that I can just rattle off that would make me change my mind. We all should. You should think about that. What things would change your mind so that if somebody asks you again, yeah, these things, and they should be reasonable things, not just
let me tell you one thing. Okay, so I just recently I was a big fan of what's his name? He does all the ancient history stuff. I forgot his name now. He was on the Joe Rogan podcast, and basically, anyway, I follow him. I like him, and I think he's quite reasonable. But then he gave the argument that he was talking about flat Earth, and he said you could tell that the Earth's not flat because boats disappear over the horizon bottom up. But I know there's a lot of, so for example, if someone's using that as an argument and that can be quite easily debunked, then it's kind of like, where do you go from there? Because I've seen that being debunked. I've seen things disappearing bottom up in like experiments, like on a table. So it's kind of like, if that's your
Richard,
someone like him,
go get those videos.
Graham Hancock, that's his name.
Go get those videos. Go get those videos on the table. When you're at the ocean, you see the top of the ocean, right?
Go on.
When you're at the ocean, you see the top of the ocean. On those table experiments, you don't see the top of the table. They always put the camera down around the side of the table, and you do not see the top of the table. That's on purpose. All right.
Yeah, but it's just changing the angular resolution limit, isn't it? So it's just emphasizing the effect that you get.
Don't go into angular. You don't understand the topic. TBL Astro says 5 months now. Thanks, Siggy, for the constant gifted membership. Gifted sub. Any Barb's B says thanks for the gifts. I'm almost done. We got non-existent.
By the way, I do understand Rayleigh's criteria, so that kind of explains things disappearing.
No, Rayleigh's criteria does not explain anything disappearing. Rayleigh's criteria explains things not being resolvable. That's just not seeing the detail. That's what Rayleigh criterion is.
Well, but then you can see how things, the objects, the laser, the two lasers merge together, and they merge together in the central point where you can kind of see that if that was.
But they don't disappear. You still see a laser, right?
Yeah, but you can still see that as it resolves, it goes bottom up.
All right.
So it does explain the effect is possible, and that was my point.
All right. Non-existent says gifted membership train. Woohoo! Pat in the chat, who said something earlier, said, "Rich, it seems like there's evidence. There's an evidence guard on your word salad bar." That's
Go on, what? An evidence guard.
Evidence guard on your word salad bar.
Sorry, what's an evidence guard?
So when you go to a salad bar, there's a sneeze guard.
A sneeze guard. We don't get them in England.
Do you have buffets?
Yes, we don't have sneeze guards.
You don't have a plastic sheet in front of it so that you can't spit your.
Okay. Oh yeah. Okay. Yeah.
That's a sneeze guard. So
right.
All right.
I still don't get what you're
saying.
Crashes
says, "Can this flurf give me the numbers required to make a digital sundial on flat Earth?"
I can. Just give me £80 million a day, and I'll do it for you.
Don't need. Oh my gosh, people figure it out for free. Industrial Nerd says, "Once upon a midnight."
I want £80 million a day.
Well, so do I. Once upon a midnight dreary, while I pondered weak and weary over many a quaint and curious volume of forgotten lore.
Okay. Do people pay?
Something, nevermore.
Are people paying you to read this stuff out? Or
that was
giving you? Is it super chats?
That was a member chat, so he's been a member. He gets a free one for this stream. Trash Vulture. Wisely. Trash Vulture lies. Well, yeah, I mean, it sounded like that was a poem from some poet.
Okay, perhaps it's Raven. I don't know.
It may have had something to do with ravens, and not the old Disney TV show. Not understanding how margins of errors work is wild, says Trash Vulture lies. Okay. Ooh, we got it. We got a top. We got a big one here. MB says the audacity of this fool slagging off Brian Cox.
Yeah. Did you say I'm slanking off Brian Cox?
Slagging off, yeah.
Yeah, he's not a good guy. Just you don't need to worship him like he's your god or your deity. Just
we don't. That's put on us from other people, but he's just a guy
he's a bit of a loser
with the same accent as you.
Yeah, he's not got the same accent as me.
As far as that's all I can tell. Anyway, why, as Delco says, why listen to Witsit instead of Every Scientist?
Yeah, I listened to. I did actually used to listen to him, and obviously I did follow a bit of Neil deGrasse Tyson. But
to Witsit,
I'll listen to anyone, mate. Honestly.
All right.
If I think they're sensible and they're worth listening to, I'll listen to him. But if they start spouting off and start,
I'm over time here. Let me. Alyssum says, if you think the Earth might be flat, can you explain why we have to count for the globe whenever we calculate our flight distances?
Do you?
You do.
Do you?
Yeah, you have to use.
What about when pilots go on autopilot?
When they calculate flight distances, they need to know how much fuel to put in the plane. There's no autopilot for calculating how much fuel to put in the plane. Like you need it, right? I mean, there's software that does it, but it uses the Haversine formula.
Right. Cool. Nice.
I've never gotten flat Earth distance between points formula. You'd think it'd be the polar distance formula, but it's not. It doesn't work.
Well, I can't imagine it would be too far out because the north's pretty much the same. It's only when you get into the south the distance.
That's a bit of a problem, though. Anyway, Aaron Reese says, if things disappear bottom up, then why do camera lenses not have a stronger zoom at the bottom? Oh, that'd be great. It'd be really cool.
Camera lenses have a stronger zoom at the bottom.
For like the lens, the P1000, then maybe the P 1100 has the bottom half of the lens has a progressively stronger zoom than the top. That'd be fantastic. Might be a little bit of a challenge.
So what's the point? What's the point? Like you'll be able to bring it back into focus.
Yeah, well, I mean, because people claim that zoom brings things back, even though there's no examples of that whenever I ask for it. But I think it's tongue in cheek.
there are some examples of like the sun going over the horizon. It looks like it's setting, and then you zoom in, and then you can actually see the the point where the bottom of the
No,
sun
no.
and the ocean, for example, join. You can
Here's
see there's a gap there.
yeah. How about this? The sun sets completely, and then you zoom in, and it comes back. That's
But then
not
you've got
happened.
issues with the atmosphere and
That's
stuff.
never happened.
Yeah, it won't happen. There's the atmosphere to get through. Come on, you know
No,
this. It's like this is a bit of a straw man. You know, there's like
no,
atmosphere there and stuff like
no,
that. So, yeah,
no.
come
That
on,
doesn't
Michael.
work.
You're
That's
not
not
going to
how it
get me
works.
on that one
Because
because this
immediately
is where you
above
lose me because we know that light
Richard,
doesn't travel forever.
immediately above the horizon, 6 hours later, you can see the stars immediately above the horizon, and they're not blocked.
Yeah, because the atmosphere they're closer to the surface is a lot thicker, it's a lot dense,
But
isn't
the
it?
sun,
So
but you can see the stars, which are much
yeah,
less
because
bright than the sun.
yeah, but there's not got the whole atmosphere. And to be honest, I don't know what's happening with the stars in the sky. It's quite interesting, but I know that if you
Kind of
look
falls apart. All right,
through a chimney, no,
all
if you're
right.
looking through a chimney, for example, during the daytime, you can see the stars. So whatever
Yeah.
happened there, it's
And
weird.
that's what James Bradley was doing. Um, Silver Phoenix Rising says we don't go into the water or underground to see things in the far distance disappear bottom up like those videos show on a table.
Oh god, everyone's going on with this. Bottom up
Yeah.
now. Yeah, just one sec.
Hold on. Jolene says, did you say that poem was from some poet? It was a poem that was from a poet. Did you know that? Charles Arnold had a member chat but didn't write anything fact based. Says, yes, I paid to call you stupid. You are N I can.
See, now you've lost me. You've lost me. Bad guy, bad guy. You should get a bit of respect. To be fair, like I know a lot of people that wouldn't have the balls to come on and discuss this stuff.
I appreciate that
so
for sure.
I think that guy needs to man up and
All
stop
right, man
being
up, fact based.
insulting. Yeah.
Special message from Richard.
Stop being mean. You mean little boy. Be nice. I'm providing you good entertainment here, so you got to be nice.
Ringo Starr accent. Never mind. All right. 3 Ron says lots of mental gymnastics denying experiments. Well, I sent it to him, so he'll
mental gymnastics denying experiments. Well done. Very good.
All right. MB says no worship. This is I think about Brian Cox. Just respect for his knowledge, which you clearly lack. And then the final one. This is it.
Well done.
Said Silver Phoenix Rising said, if Earth didn't rotate, the sun would never set. And yes, I agree with that.
Of course it would.
So, all right, I gotta get going.
But that's subjectively wrong as well. Because
all right, do you know what a Poe is?
A Poe? It's like a ghost.
No.
A Poe, is it spelled P-O-E?
P-O-E.
I'm googling it now.
Just Google Poe's Law. Poe's Law. All right, I gotta get going. I gotta jump in a car here and bring somebody somewhere. So, Richard, thanks for being a good sport. Anything you want to say as we pop out?
Yeah, no, I appreciate you having me on. I really enjoyed it. It's been a laugh, to be honest. Yeah, I hope we keep in touch and you can keep sending me bits and bobs that you find along the way on your journey. And yeah, I'll be interested in speaking again. And I thank the audience for being very respectful, apart from that one really mean guy. But apart from that, yeah, it was a lot of fun. And yeah, I'll speak soon, I guess.
All right. Awesome. Thanks, Richard. We'll see you.
All right. See you later.
Bye.